इसको ना
Could I request the attendees standing up there to sit down, perhaps, and see if there's enough space for you to sit down? हाँ?
मेरे को सबको बोलना पड़ेगा मेरे को इनको सिक्योरिटी को कहीं पीछे रहेंगे तो दिक्कत होगी
क्यों दिक्कत क्यों?
विंडो में वो शीशे बात रखी हैं तो हिलेगा पैसा
And there's a request that you don't put hands on that on the glass because it's a little flaky. So, and the same request goes for students and faculty members here. If you could also sit down and possibly, I think this room is overbooked now. So Professor Haroche will be coming in soon. So we'll start the session shortly.
Okay.
अभी सब प्रेजेंटेशन देंगे.
Good afternoon, everybody. We are already 7 minutes late. It's quite a turnout, I must admit. And it's quite a surprise. We are very, very happy that the room is overfull, but sadly we can't. We only have that many seats. But any case, so let's get started. I am Narayanan Kurur, and I would like to request Professor Rangan Banerjee, the director, to say a few words and welcome the chief guest and other dignitaries. Professor Rangan.
So it's really a pleasure on behalf of the IIT Delhi community to welcome our speaker today, Professor Serge Haroche. We are delighted to have you here, sir, and you can see that the turnout is much better than we expected. We should have had another venue, but we didn't have time to change the venue. So we hope that our interaction with you today will encourage you to come back to us, and so that we can interact with our young students and our researchers. And we look forward to hearing from you on the science of light. I'm also delighted to have with us today our partners from the French Embassy and from Cefipra, and also other distinguished guests. And I'd like to once again welcome you all to IIT Delhi and look forward to an interesting session. Thank you, sir.
This event has been made possible to a large extent due to the collaboration, as the director said, the French Embassy and Cefipra. So I'd like to have Professor Nitin Seth, Director of Cefipra, to say a few words.
Thank you, sir. I'll not be becoming an abstraction between the photons and the students and the enthusiasts. So I would be very brief on that. So thank you very much. IIT is my home. I am an alumni of IIT. So it's just like coming back to home. It's always a delight and pleasure for me. So thank you very much, IIT, for hosting us, providing such a beautiful gathering and audience. I'll not be taking much time on talking about Cefipra. Cefipra is actually Indo-French Center for Promotion of Advanced Research. So probably all the researchers, please, I would request, I'll come some other day for talking about Cefipra. So I'll not be becoming an abstraction, but do look at the websites. We have a lot of calls for students' mobilities and the researchers' mobility. Thank you very much. Thanks once again.
Thank you. So what is planned for this evening is that Professor Serge Haroche has recently published a book on the science of light, which he would talk about for a little bit, and then there will be a panel discussion revolving around the book. So it is not an institute lecture in the normal sense. So what I'll do is I'll first introduce Professor Serge Haroche. Most of it is available on Wikipedia. But what I have to say is something that I have lifted from his own words in the National Academy of Science membership, where he says that my main research areas are in quantum optics and experimental quantum information science. I have made many contributions to cavity quantum electrodynamics, the branch of quantum optics studying the interactions of single atoms with photons inside high-quality Q-factor cavities. And it goes on. I've given you where I've lifted it out from. You can read the rest of it from the NAS website. In addition, William Phillips, who was a co-Nobel laureate with his supervisor, Claude Cohen-Tanuji, has this to say. He says, this is, again, writing about him and David Wineland. He says, Wineland and Haroche realized a long-standing dream of quantum physics, studying the behavior of single quantum objects. The founders of quantum mechanics believed that studying a single quantum system, like a single atom or a single photon, was beyond the realm of experimental possibility. Many believed that it did not even make sense to talk about a single atom. Only the behavior of an ensemble could be meaningful. In fact, Schrödinger asserted, we never experiment with just one electron or atom. In thought experiments, we sometimes assume that we do. This invariably entails ridiculous consequences. And so William Phillips goes on, and then he says, after he talks about Wineland, he says, Haroche did much the same thing, but trapping photons, particles of light, in a cavity where the photons bounce back and forth between two mirrors 1 billion times before escaping. Cooling the mirrors to less than a Kelvin nearly eliminates the thermal photons in the cavity, so Haroche's group could study one or a few photons that they deliberately put into a cavity. In any case, so that's, you can read about it in most of the places. That is again on the PNAS website. So he is, well, a student of Claude Cohen-Tanuji, who is also a Nobel laureate, who in turn was a student of Alfred Kastler, who was also a Nobel laureate. And all of them worked at the Laboratoire Kastler-Bruxelles. So that is something for all of us to emulate, a genealogy where there are 3 Nobel laureates. If we ever get there, then we can be proud of something. So that's Serge Haroche for you. The panelists this afternoon are Fabien Charret, Fabien is the attaché for scientific and academic cooperation at the Institut Français, Delhi. He is also a philosopher, having been trained at the University of Paris, Sorbonne. The second panelist is Professor Anurag Sharma. Anurag Sharma, for the youngsters amongst you, is a homegrown product, having done his MSc, MTech, and PhD, all at IIT Delhi. He works in optics, and he is a Shanti Swarup Bhatnagar awardee. Professor Kedar Khare. Professor Kedar Khare is in the Optics and Photonics Center, and he works on optical imaging. He is a graduate of IIT Kharagpur and the University of Rochester Optics Center, which is, for those of you who don't know much about optics, one of the top places in the world for optics in the US. And Don de Cruz, the youngest member, is a philosopher of science. He is from the Department of Humanities and Social Sciences, and like every other South Indian, started his career in engineering before he decided philosophy was So after a lot of ado, may I request Professor Haroche to introduce his book.
So thank you very much for this very kind introduction, and you said a lot of things, so I will be rather brief. It was supposed to be a conversation, so I will just try in a few minutes to introduce the book by explaining why I thought it was interesting to write about the history of light. In fact, of course, the main reason is that I have been interested in light during my whole scientific career. I have been working, as has been said, about the interaction of light with atoms, and at the most fundamental level, what you can expect when you have a single atom interacting with a single particle of light, which is a photon. And this has led me to do interesting experiments, but also, and most importantly, I think it has also led me to interact with a lot of colleagues working all over the world in fundamental physics about this problem in optics, quantum optics, interaction of atoms with light. And during my career, I have witnessed a fantastic evolution of the field. I have been lucky to start working at the time when the laser was invented back in the 1960s. And I immediately understood when I was doing my thesis work with Claude Cohen-Tanucci, which has been mentioned in the presentation, that lasers would open fantastic ways to do physics, that it was a tool which would allow us to do things which are impossible to do with classical light. And we imagined that, we had this intuition, but even our imagination could not be at the level of what has been achieved during the last 60 years. I will give you only two examples. One is that the gravitational wave detectors, the antennas which allow us to detect the ripple of space-time produced by the collapse of neutron stars or black holes. These devices are able to see, to measure differences in the distance between two mirrors which do not exceed 1/1000th of the size of an atomic nucleus over a distance of 4 kilometers. And this is achieved by having in the interferometer circulation of laser light, very stable laser light. And this took 50 years to achieve. In fact, these experiments have started at the time I was starting my own PhD, and it took 50 years for the experiment to come to fruition. Another example are the optical clocks now, which measures the optical frequencies of a laser which is locked to an atomic transition. These clocks are now so precise that they can observe the gravitational redshift over a distance of 1 millimeter at the surface of the Earth. This was absolutely undreamed about when I started my own career. So about a few years ago, the editor Odile Jacob pushed me to write a book about this, and I thought about this, and I decided that it would indeed be interesting to write a book about the history of light. And this for many reasons. First of all, because I had my own interest in that, but most importantly, because I think that the history of the science of light, the way the ideas about light have evolved over the centuries, is intimately linked to the history of science itself, to the development to the birth of the scientific method, which is based on observation, experiment, theories predicting new observations. If these observations are made, then the theory is vindicated. If these observations are not made, then you have to abandon the theory and to look for something else. And this has been the constant history of light over the centuries. It's also fascinating because this history has involved a large number of very bright minds, not only scientists, but also philosophers. If you just look at the 17th century, you had Galileo, which started the whole story, and Newton, but you had also Descartes, who was a philosopher and was, as we know, one of the theorists of the rational thinking, which is so important in science. And then in the 19th century, you had Faraday and Maxwell and Ampere. And in the 20th century, of course, you had Einstein, Bohr, Heisenberg, Schrödinger, and Feynman. So really the bright minds in the history of science in general have been interested in the history of light. Now, this history is also important because it emphasizes some points I would like to stress. Light, you said in your introduction that there are people who are not specialized in optics, but in fact, we are all specialized in optics because most of the information we get from the outside world comes from light. We need light to get information about our surroundings. In science, light was a vector of all the information we get about the universe. The motion of planets, of stars, and so on, were observed since antiquity, since the prehistoric times, and light plays, of course, a major role in that. What is paradoxical is that people used light all the time, but they did not know what it was about. And in the prehistoric time, since the prehistoric time, light has been considered in religions and mythology. Even in the Greek antiquity, the ideas about light were very fuzzy and were not based on observations. They were based on some preconception ideas. But the knowledge about light has become really scientific, I would say, from the 16th and 17th century, when measurements have become possible. And so the connection between the knowledge about light, which is knowledge which is triggered by curiosity, we want to learn, to understand what light is about, this knowledge has been able to build up when technology has given us the tools to make quantitative measurements. And what I try to discuss in the book is that the first quantitative measurements about light, the one which have started the theory of light, came with Galileo in the 17th century, when he developed the first, he used the first telescope, the Galilean telescope, to look at the stars and make quantitative measurements. And he was at the start also of the pendulum clock, when he understood the motion, the properties of the motion of a pendulum clock, which was developed by Huygens a few years later. So the telescope and the pendulum clock made the start of all this, because they allowed for the first measurement of the velocity of light. Up to Galileo's time, people saw that light was so instantaneous that it filled all space immediately. Galileo was the first to doubt that, and he said, to measure the velocity of light, he put one of his assistants on a hill. He was standing on another hill in the Tuscan background, and he had a lantern. He uncovered his lamp, and he asked his assistant to do the same when he saw the signal. And he was expecting that there would be a delay for the light to go back and forth between him and his assistant. Of course, he did not observe anything, because the delay is of the order of a microsecond, which is much too short to be detectable. But so he gave up this idea and did not think about that anymore. But in fact, by using the first telescope and inventing the pendulum clock, he gave the tools which allowed 60 years later, Römer was an astronomer in Paris, to measure the velocity of light. And I remind you, the way he did it, Galileo had discovered the satellites of Jupiter. The first time he pointed his telescope toward Jupiter, he saw that there were 4 small spots going around Jupiter, which are the satellite of Jupiter. And of course, this was a fantastic discovery by itself, because it was the first observation of a planetary system, and he just vindicated the ideas of Copernicus. So it was very tricky for Galileo, because it was difficult to assert this in front of the Pope and the Catholic religion. But so he did not say much about that, but he made the remark that these satellites were a kind of natural clock, which could be observed from anywhere on the surface of the Earth. And the first idea was to use it as a navigation tool, because you could see the hour measured in Paris by looking at the tables that Römer made of the reapparition of the satellite of Jupiter coming out from the shadow of the planet. And this table was used by navigators to compare the time in Paris with the time where they were, which is the first measurement of longitudes. And this was the ancestor of the GPS system, in fact. But more importantly than that, Römer realized that each time Io was coming out of the shadow, took a little bit more time than the previous time, or a little bit less time. And he realized that this was the time it took for the light to propagate along the distance that the Earth had gone away or back towards Jupiter during the time that the satellite was making one turn. And from that, of course, he needed to know what was the size of the Earth's orbit around the Sun. And quite by chance, this distance had just been measured by one of his colleagues at the Paris Observatory. This colleague was sent to Cayenne, to Guyana, and looked at the planet Mars. And they looked at the parallax, the difference of direction of Mars being seen from Paris and from Cayenne. And by triangulation, they got the distance from the Earth to Mars, which allowed him to get the distance of using Newton's law. So all this converged to get the first measurement of the velocity of light, which means that, in fact, optics and mechanics and the planetary equations of Newton were important to make this discovery. What I want to make, why I made this long story, is just to tell you that if Huygens' pendulum had been only 1 order of magnitude less precise, he would not have measured it. This pendulum kept the time with a precision of about 10 seconds per day. And 10 seconds is about the time that the period was changing every day. So it would have been impossible with a less precise clock. And we can extrapolate today. Today the clocks are billions of times more precise, and they observe phenomena that they could not observe if they were a little bit less precise than what they are. So physics and science in general is a constant race between the precision of instruments and the theories which evolve with time. So I could go on and on. I want to give you another example of that. The guy who went to Cayenne to measure the parallax of Mars was carrying a clock by one of Huygens' pendulums, and he realized that the period of the clock was a little bit slower in Cayenne than it is in Paris. And Huygens was not only an engineer, but also a great physicist, immediately realized that this was due to the centrifugal force, the fact that at the equator, the point on Earth is rotating at a higher speed than it is at the latitude of Paris. He made the computation, and he found, yes, this explains, but it explains only half the effect. And then Newton and Huygens realized that the other half was due to the fact that the Earth must be oblate. Because of this rotation, when the Earth was not really solid, it should expand at the equator. And so a point at the equator was farther from the center of the Earth than a point in Paris. And so this was one hypothesis. To resolve this problem, the French Academy of Sciences sent 2 expeditions, one in the equatorial region in South America, and the other one near the polar circle. And they measured 1 degree, the distance corresponding to a difference of 1 degree of latitude at the pole and the equator, in order to find out whether the Earth was oblate or not. I must say that these expeditions were very dangerous. The expedition in South America lost many members. It cost a lot of money. It took them 10 years to get their measurement done. On the polar circle, it went much faster. When they came back to Paris, they realized that the Earth was indeed oblate. This, I think, was one of the first big scientific projects. The King of France spent a lot of money on that project, which is, you can compare it now to big projects like big telescopes or the CERN and so on. You see that at that time, the governments were ready to spend money for the prestige that it gave to the nation which was making this kind of experiments. And of course, the fact that the Earth is oblate is an important result in geodesics. And when Maupertuis was a leader of one of the expeditions, reported about it, he explained that this was not merely to satisfy some kind of idle curiosity, but it might be very important for the science of astronomy and navigation. So he already had in mind the fact that you have to justify your work to give it some kind of utility. And this is something which we realize now when we have a project, a research project to present. So I could go on and on, but the only thing I want to say also is that eventually, in the end of the second part of the 19th century, it was discovered that light was an electromagnetic radiation. And this discovery was made because Maxwell realized that the equation of electricity and magnetism allowed him to calculate a velocity of propagation, which was exactly the one which Foucault in Paris measured for the light. And so he said, this cannot be a coincidence. It means that light is an electromagnetic radiation, and there should be radiation which are invisible in the infrared and in the UV, and this led to a lot of applications. So you see, again, the intrication between basic science theories and experiments which converge to give you a deeper understanding of the world. After Maxwell, the experiments became more and more precise, and the scientists realized at the end of the 19th century that there was something wrong about the classical explanation of the thermal radiation and about the classical explanation of the existence of a medium called the ether to propagate the waves. And this gave rise to the revolution of quantum physics and relativity. And we live in this world now. All the instruments we use in our daily lives are based on our understanding of quantum physics and relativity. And all this came from light. So light is not only illuminating us around us, but light has illuminated our understanding of the universe and plays an essential role in all these aspects. So I think I have spoken too much, and I might answer to questions relative to that. Thank you.
Thank you so much, Professor Haroche. So I think Leibniz, in the new essays on human understanding, says about Christian Huygens, we will call him Huygens today, he says in Latin, solem dicere falsum audet. He dared saying the sun was wrong, precisely by using the clocks that you mentioned, and to sort of turn down the accuracy of the cosmic clock that was until then always the reference. It signified some sort of new era of technology entering the world of our scientific calculations, and so it's very important what you said about Huygens. So thank you so much for this presentation. The session here is about the book. Before that, I want just to say a few words. Barely 21 years old, Serge Haroche in Paris made a difficult decision after much reflection. He was trained, of course, in the high school in the classical mechanics. He had his eyes wide open on special relativity and all the new theories that were happening. And he made the decision, though France, as you mentioned in your book, France's colleague told him, oh no, don't do that. It's a very old science right now, more than 70 years old. Why would you do that? You just have to calculate, nothing new to be discovered. And it was exactly the same words Arago said to young astronomers in the 19th century when they came to say, oh, we want to do astronomy. Why do we do that? Laplace was there. He said everything that is to be said. Don't do it. So living and pursuing his dreams, in his passion for certain aspects of physics, Serge Haroche went to atomic physics and dedicated his life to this craft. And of course, it happened that changed the face of quantum physics as we know it. It changed it considerably. We're here to discuss this thing that happened, and that is reflected in the book, which is at the same time a promenade in ideas and notions, the notions of light, the one that historically appeared, to shape progressively the concept of light and the things, the achievements that were done when Serge Haroche took charge of different labs where he was working, and the experiment, and the way he discovered to actually control and manipulate sort of individual quantum systems, which is something revolutionary. So the book is about this journey between ideas and also back the journey of one individual, Serge Haroche himself, of course, and the way it is written drives us from classical mechanics to, of course, the new avenues and possibilities at the end of the book that are opened by quantum technology and all the like. We are gathered here to talk about this book. I might say that Serge Haroche, we're very proud of having you, and I give the floor then to the panelists. You're one of the 14th Nobel Laureate in physics, French Nobel Laureate in physics. It's very rare indeed to be able to talk to someone with your stature. And I think we have gathered here a panel of professors who are interested in various aspects of the book. And I give the floor right now to Professor Sharma, Professor Sharma, I think you want to highlight some historical perspectives on the book. I'll give you the floor.
Hi, good afternoon. Thank you, sir, for agreeing to interact with all of us. I will not claim that I have read the book completely. I acquired the book only 2-3 days back. I have read some portions, and it's really fascinating. I mean, I must say that the portions that I read, the way it is written, as if, there's a flow of history just going on in that book, and I will read quickly the entire book, surely. Yeah. No, my question is regarding, you just mentioned about Maxwell, and which was kind of culmination of the classical viewpoint of light. But most of it started with Huygens, Christian Huygens, who gave the wave theory. And but there was something lacking in his wave theory, because it had to wait 100 years for Thomas Young to do the experiment and come to the full wave theory. So my question is, what's the difference between those two thought processes, Christian Huygens wave process and the Thomas Young, and why did it take 100 years? There were so many bright minds in that time. Why did it take 100 years to do that? Yeah.
That's an interesting question. I think, first of all, I think Christian Huygens is underestimated. Of course, in the 17th century, you have two giants, Galileo and Newton, and Huygens is in between. But he was a fantastic engineer, and he was a very deep physicist. He discovered the centrifugal force. He built this clock. He was an astronomer. He discovered some Saturn rings. And he was a much nicer person than Newton, I think. You could have Huygens as a friend. I don't think you could have Newton as a friend. And he was working in Paris, which is not bad. But when he wrote the theory about light, he was exiled to the Netherlands because he was a Protestant, and at the end the King of France has banished the Protestant from the kingdom. Nevertheless, he wrote the Treatise of Light in French and dedicated it to the king, in spite of the fact that he was expelled. He did another thing which is very important in modern physics. He discovered the fact that when two pendulums are weakly coupled with each other, they synchronize. And the synchronization clock gave rise to what is called the mode blocking of lasers, which is a very important phenomenon in modern physics. So he's a very fantastic person. But of course, in order to see the interference of light, you need to be able to to see phenomena which happen at the wavelengths of light, which is very, very short, micrometers. And so you need to have the interferometers which are precise enough. But it's true that he could have done Young experiment earlier, because the technology at the time of Young and Fresnel was not that much better. Maybe one reason is that Newton had the other view. Newton said that light was made of particles, and Newton was much more famous because of the triumph of his theory of gravitation. And so in the whole 18th century, most scientists followed Newton and did not question the fact that light was made of particles. So maybe that's one of the reasons. And of course, when Young did his experiment, he was able to deduce from what is also very strange, that Newton had a very good description of colors, the fact that Newton rings, for instance, and he gave a good description of colors in spite of the fact that his particle theory was unable to explain the colors. But he had made precise measurements, and Young had only to take the values found by Newton to deduce from that the wavelengths of light, and knowing the velocity of light to deduce the periods of light oscillations. I think in Young's book he has the first table which says that red light oscillates at 400,000 billions oscillations per second, which is a quantity which was absolutely impossible to access with by experiments. And these are precisely the frequencies that the optical clocks measure now, 200 years later. So it's fascinating to understand that. Another thing about Newton versus Huygens. According to Huygens, the light was a wave, and in this case, his theory said that when light is going from air to water, the wave crest should be closer in water than in air. That means that light goes slower in water than in air. Newton said the opposite. He said when light is reflected, it means that the particles are sucked in the water and they go faster. So there was a clear-cut difference which needed an experiment to be done. But the experiment could be done only in the 19th century by Foucault, who looked at the time it takes for light to propagate over 7 meters in air and in a tube of water, and he found that light was slower in water than in air. And what Foucault did was to take back the old idea of Galileo, which is to uncover a light beam and to look at the time it takes to come back, except that he didn't use an assistant. He just put a mirror, which is much more, reflects faster, does not take any time. And he had very fast choppers, which Galileo did not have to put the light on and off, which again shows that technology is useful. Galileo could have, the principle Galileo had, it was doing that, but in order to do it in a lab at a short distance, you need to have very fast mirrors, and this is what Foucault had. And then this measurement not only proves that Huygens was right and Newton wrong, but it also gave the figure that Maxwell, a few years later, used to make the remark that the electromagnetic waves were light, in fact.
No, see, just one minute. My precise question is that did Huygens know that the wave will cancel another wave?
I am not sure, because he never used the word wavelengths. He said that light is a kind of disturbance.
Yeah, it's more like a wave of people, coming like in an army or something like that.
Yes.
He was not looking at plus and minus, probably.
No, this had to wait for Young.
Yeah.
And I must say, Fresnel is also very important.
Of course.
Because Fresnel found that the light is a transverse vibration. Yeah. And moreover, I think Young was a fantastic experimenter, but he did not make the mathematical calculation that Fresnel did. Fresnel used calculus to find the exact law of diffraction, and also he introduced complex numbers into physics, because he said that to explain the amplitude and the phase of the wave, you have to use C numbers and not real numbers. So it was also a very important point.
Thank you.
Thank you. I think also Fresnel was the type of mind that we find in the core of the engineer, the French engineer who was working with the military, and had that particular mind that Young didn't have, maybe was more of another figure of scientist. But that's an interesting point for me to introduce Professor Kadakare with some questions about the transmission of the knowledge.
Yeah, sure. So, as already Professor Kurur mentioned, that you worked for your PhD with Professor Cohen Tanuji, and so many of the physics students here are actually familiar fans of the quantum mechanics books.
Yes.
And so it will be very nice to know what was the environment in the lab and how you got in touch with him, and what was your experience working with him in general?
Yeah, when I joined the lab, he was a very young professor there. He just had been named professor at Paris University, and the first course I followed from him was a course on relativity, and I found it fascinating, and I was so enthusiastic that when I came back at École Normale, I just repeated the course in front of students who did not follow it and tried to follow his ideas. And then I heard that he was giving also a course in quantum physics, and I just joined this course, and it was also amazing. And then a couple of years later, he started writing this book with Dieu and Lalouet, and I witnessed the way the book was. I did not participate at all, but I witnessed the discussion. They spent 6 or 7 years to write the book. This book is organized in a very nice way. You have a chapter in which the principle and the basic ideas are mentioned, and then you have complements in the end with exercise problems completely solved, which go deeper and deeper in the explanation of the book. I must say that he also wrote, there were 2 volumes, and then I think 15 or 20 years during the last 10 or 20 years, he wrote a 3rd volume which includes these new ideas about quantum information, quantum entanglement, and the second quantization, and so on. So he spent a great part of his life in the writing of this book for students all over the world, and I know the book has had a lot of success. At that time, he was in the lab. There were two other famous people: Alfred Kastler, who got the Nobel Prize for optical pumping, and Jean Brossel, who was an early student of Kastler, who was a very deep mind too, and nobody understands why he did not share a Nobel Prize with Kastler for optical pumping, because they both worked on that. I think Kastler got the prize in 1966, and I am quite sure that he met Raman at the end of Raman's life, so there is some connection with India. Kastler had an international mind. He interacted with a lot of people, and he interacted in the Pugwash movement against the use of nuclear weapons, and he might have a connection with Raman in this context. And so it was a fantastic experience to be in this kind of laboratory where people were able to discuss freely, to exchange ideas. We did not need too much money to do experiments at that time, and we did not have to write proposals. There was no bureaucracy. We did not have this need to fill up Excel forms and to ask for money and so on. I just went to see Brossel and I said, I want to do this experiment. He said, okay, write me half a page, and then he gave me the money I needed for that. So that was a really fantastic time. Then I went for a postdoc with Arthur Chalot in Stanford, and the spirit was somewhat different. The atmosphere was apparently more relaxed because it's the American way of doing physics, but it was also very deep and very interesting. And Chalot liked to joke a lot, but he was doing serious physics too. For instance, one day he had the idea to build a laser using as the amplifying medium this kind of jelly that the Americans like for their breakfast. So there was a dye, a green dye or a red dye in the jelly, and he could make it laze exciting it with a laser. And so they published a paper about the first edible laser. It was in 1972 or 73.
So that's very interesting that you didn't have to write proposals, and now I think many students are also becoming part of that machine. So one slightly technical, I would like to, meaning, when we see a lot of your work, the central theme or central concept is the vacuum fluctuations, and it's very difficult concept for students to understand many times, or also for the teachers probably. And could you kind of elaborate on this concept a little bit, and for the benefit of all the students?
So that's one of the principles of quantum physics, the uncertainty principle, the fact that you cannot measure with infinite precision at the same time the position and the momentum of a particle, and that there is uncertainty. You have to make a kind of compromise between the precision of the measurement of position and momentum. And this is important because it is also deeply connected to the principle of complementarity of Niels Bohr. If you could make with precision both measurements, then you would have a contradiction with the fact that you cannot have at the same time a trajectory, which is a well-defined position, and interference, which relies on the phase, which is related to the momentum. So these ideas were developed at the time of when Bohr and Heisenberg discussed with each other back in the 1930s, and a lot of thought experiments were imagined by Einstein to try to find a way around this uncertainty principle, and he never succeeded. In fact, you have to admit that. But this means that if you take an oscillator, you cannot have the oscillator in the ground state, which is motionless at the bottom of the trap, because then the position and the momentum would be known. So the oscillator must have a minimum motion, a minimum non-zero energy due to this principle. And now the field, the electromagnetic field, is made of oscillators. What Maxwell has shown, that the equation which describes a field
are the equation of oscillators. The electric and magnetic field plays a role, so to speak, of the position and momentum. So they cannot be both zero because of that. And you have a minimum energy, which is called the fluctuation of the electromagnetic field. And if you want to give yourself a classical picture, you have to admit that you have random fluctuation of the electromagnetic field, which fills this vacuum. And in fact, this has been observed. If you look at very precisely at the energy levels of an atom, you find that they depart from what a quantum mechanical calculation would give you in the absence of these fluctuations. There is a small shift of the energy levels, which is called the Lamb shift, and which was observed by very precise experiments back in the 1940s. And again, there is a strong connection between basic science and applied science, because Lamb was able to make this measurement with microwave sources of radiation, which were developed for the radar during the war. So it was the source which were developed for practical applications and military applications were used for basic science. Now, one of the physicists, which in the 1930s was the first one to make to describe the importance of vacuum, was Hendrik Casimir, a Dutchman. And Casimir was a theoretical physicist, but he became later on the CEO of the Philips Labs, so he knew also about applications. And he wrote a famous sentence in an article about the stupidity of separating basic science from applied science, which is one of my main line of when I give a talk like this one, I emphasize this. He said that there is hardly any invention which is not based on basic science.
I think now it's time for some other kind of questions. We had the historical part, more about the science and its making. So I think, Professor Don de Cruz, you want to dig more about the entanglement of philosophy and science, not of particles. So I give you the floor.
It was a pleasure reading your book, Professor Haroche. And so far my favorite chapter is chapter 2, and that's because I never got to chapter 3. I'm pretty sure that's going to be my next favorite chapter. But I thought chapter 2 was interesting because the optics debates of the 17th century, it's very fascinating. So on one hand, you have Descartes, who's an intellectual giant, and he wrote something like Meditations of Philosophy. But then the interesting figure for me is Newton. So Newton's not a philosopher, but in doing science, he did make a distinctive approach in giving philosophical arguments. So for example, from his experiments on light and the phenomenon of colors, he said, the colors are properties of lights, substances are those that bear properties, waves are not substances, and therefore light has to be a particle. So that to me seemed a philosophical argument. Of course, he tried to make it consistent with empirical data. And looking back, we might say, yes, they had to make such philosophical arguments for the lack of good theories that we now have, or for the advances that we've done in terms of experiments. But do you think this approach, the Newtonian approach of taking a philosophical employing certain philosophical arguments to take a scientific position, does it have scientific value? Have you seen avenues of that approach in your own work? Have you seen physicists in the contemporary times doing what Newton did back in those days?
I think it's a deep question, and people have different answers to that question. I remember I wrote a book by Steve Weinberg, who is very despiteful for philosophers. He says there is hardly any philosophical idea which has helped science to progress, and he's very much against that. On the other hand, you can say also that Einstein had some philosophical preconceptions. When he developed the theory, in fact, he was at the start of the quantum physics with his wave-particle duality for light, but he never admitted he understood the consequences. He understood that this was introducing non-determinism in science, but he did not like that idea. And he kept the rest of his life fighting against that, trying to find loopholes in the quantum theory, or to say, as he said, to complete it. He did not say it was wrong. He said it was incomplete because it had this undeterministic aspect to it. And he was wrong in the end. And Newton was wrong too, because he had this philosophical preconception. And I must say that also the philosophical ideas of Descartes were wrong. He thought that light was, he said that light is a kind of the stick of a blind man, that it's used to get information. So in his view, it was not so far from the view of in antiquity, where people thought that light was in fact coming from the eye to the object to get information, which is not the way it works. So philosophical ideas have often led to wrong answers, sometimes to right ones. In fact, there are another Einstein was also following the ideas of Ernst Mach. He developed relativity. Mach said that the only things that count are the things that you can really observe and measure. And this is what Einstein did for the special theory of relativity. He imagined clocks, and he used the imagination of using real clocks to observe phenomena, and he was right. And then, when he discussed with Heisenberg about relativity, quantum physics, young Heisenberg tried to say to Einstein, but I am doing exactly the same. I have put tables with the position, momentum of particles, because this is what we measure, and I don't ask myself what is the trajectory, because I don't measure the trajectory. I measure either the position or the velocity, and I have these tables that they don't commute with each other, and this led to the uncertainty principle. And he said, so I use Mach's idea too. Why don't you do that for quantum physics? And Einstein is supposed to have answered, you don't use the same joke twice. So he considered that philosophy in the end may have been helpful, but it was a joke. So I cannot answer. This debate still exists now. Some people are not happy about quantum physics because they say they cannot give themselves a picture of what's really happening. And so this word real, what does real mean? If you discuss the meaning of the word real, you enter into the realm of philosophy and not of the realm of physics. And it might be useful maybe to give you an interpretation which might be more fruitful than the one we are using today.
So let me follow it up with the problem of shut up and calculate the approach.
About what?
The shut up and calculate approach, which you talk about in the first chapter.
Yes.
And so one could say, well, either you shut up and calculate, or if you venture into interpreting the theory, you risk being misled by these philosophical ideas.
Yes.
Now, again, so I'm taking a skeptical view here. So what would be the alternative? Because on the one hand, you could say, well, the intelligibility that we get from theory, so what makes a theory successful is that it is backed up by a good mathematical formalism. It gives you empirical observations that you can verify and thereby confirm the theory. And that's all there is to good science. Now, if you go and try to interpret it and find a deeper fundamental theory to explain what you observe, isn't it the Newtonian approach? Because Newton thought, well, my laws of gravitation just describes. That's why he titled his book Mathematical Principles. And he didn't think he was giving a natural philosophy. Yes. So for people in your field, do you think that we should simply stay with good theories? And by good theories, I mean intelligible theories for what they are, and the observations that they give and how you can verify it. And perhaps we should just leave it to science to say, well, this is what intelligibility is. And perhaps over time, with advances in experiments and theories, we get better intelligible theories, and we should just abandon this idea of going for something deeper and trying to interpret something and thereby being misled by false philosophical ideas.
I don't know. This reminds me another story about Steve Weinberg. I think in the same book I was talking about, he says that one day he met a colleague in an elevator, and they talked about a bright student they had a couple of years before. And Weinberg asked the colleague, what happened to this guy? And he said, oh, he got into the interpretation stuff and he got lost for physics. So shut up and calculate had some power at that time, because it allowed physicists to understand the microscopic world in depth, where people like Einstein and de Broglie was following the same idea, became quite sterile for physics from the 1930s on, because they were obsessed by this idea of finding an interpretation which reconciles classical and quantum physics, while the physics had progressed a lot in other directions. And maybe this is why Einstein did not do anything really new since the 1930s. He tried to unify electromagnetism with gravitation and with the field of nuclear forces, but he did not pay any attention to the evolution of nuclear physics, which was very important in the 1930s. So he lost contact with the reality of physics and was not fruitful from then on. But I think this idea that you have to think about the interpretation came back to the forefront when one has become able to isolate single particles, because now you can really observe the quantum strangeness as it happens with individual particles, with isolated particles. And then some people have, again, tried to think about the question of interpretation. But I must say that no interpretation which is really interesting to understand the world better has emerged. If the interpretation gives you exactly the same prediction as the orthodox point of view, then it does not add anything. And there have been, for example, a very popular interpretation is a multi-world interpretation, which assumes that each time you make a measurement, there is a branch in the universe and that all the possibilities exist simultaneously. But this is really mind-boggling. It's completely contrary to the principle of economy that physics should also stick to, which is to try to describe the world in the simplest possible manner. And so again, it's a question of it comes down to a question of philosophy, unless you find a way to say, okay, this is an experiment, and the result of the experiment will make the distinction between this and that interpretation. That we don't have any. But I agree that it's difficult to understand, and there is a deep problem with the measurement. The fact that the measurement gives you a random result, and that you can only predict the probability to get this or that result, is a deep question, because our mind is not set to accept that. But all the experiments that you can do with quantum system and all the simulation you can do with the theory agree to tell you that is the way nature is operating.
Thank you. Professor Haroche, you have one last question before we go to the audience.
Yeah, so one short question. It will be nice if you can tell us a little bit about the kind of engineering that went into making these cavities, which allowed you to do these experiments, and also the ecosystem that existed to allow you to build such experiments.
Yeah, the cavities that we used are macroscopic cavities. They are two spherical mirrors which are coated with niobium superconducting material, so that they have to be polished with high precision to avoid scattering of light on them, and they have to be superconducting to avoid losses. So it took us many years to be able to achieve the quality required for our experiments. But you have other experiments now which are done with superconducting circuits, which are artificial atoms, coupled to superconducting cavity or to waveguide, and which have also very high quality factors. So there are many technologies which lead to that. You can also make cavity with Bragg diffraction layers on a small vertical cavities, and you have also whispering gallery modes on microsphere or micro tubes or round fibers, which have high Qs and in which you can observe this kind of cavity QED effect. So there are many technologies which have been developed to do that. And of course, you need also to have good lasers to control the atoms that you prepare in these cavities.
Thank you so much. Serge Haroche has other commitments, so we are going to go to the audience now. We have time for 3-4 questions. provided they're short. So make it count. Sir.
Sir, you are telling about Newton was also wrong at some point and then still there. Will we also be wrong about the assumption of whether the speed of light is constant in the future?
Okay, you are alluding to the test of relativity which have been made since the beginning of the 20th century. All the tests which have been made to test special relativity and general relativity have vindicated the theory, have agreed with the predictions. And so I think that it's a quite solid theory, the fact that the velocity of light is a maximum velocity with which interaction, communication can be made, and the fact that you cannot go faster than light, and that approaching the velocity of light will require more and more energy. So I think we can quite safely say that traveling to other galaxies is impossible and will be impossible unless something is so wrong in our in the present theories that we should have seen it already. What I think is fantastic, and I've been thinking about that when I wrote the book, is the simplicity of relativity and quantum physics. It started, in fact, from Galileo's ideas. It started from the principle of relativity of motion and the equivalence between mass and accelerations, which were in Galileo's ideas. Einstein had just to take these ideas and to say they apply not only to mechanics, but they apply to the whole of physics. And from then, all the rest is following. So it's very difficult to escape that. Quantum physics is different. Quantum physics is based on a lot of observations. It's much more difficult to get the principle out of a simple observation. And I think that's why Einstein was reluctant. I say in the book that he had two children. One child that he loved, which is a relativity child, and the other one, which was a rebellious child, which is quantum physics. And he tried to understand what the other child was doing, and he did not like it.
Oh, wait, sir, and you, and there was another one at the back. Wait. Sir, there must be some order here. So, sir, then sir. So make the question short, please, so that
most of the time when we measure the speed of light, it is a two-way. मतलब speed. Have we ever measured one-way speed of the light, or is मतलब if we have not measured it, then what are the assumptions which we are placing so that if we are concluding that the speed of light in one direction is same as the speed of the light in the other direction? Have we measured one-way speed of the light ever?
I have not measured myself, but in fact, Michelson did a very important experiment when he tried to find out whether the velocity of light was the same in different directions with respect to the motion of the Earth through what was called the ether. And he was not able to find any difference between the directions of light. And this was a puzzling point at the end of the 19th century, which was solved by Einstein. But in fact, Einstein did not pay any attention to Michelson. In fact, he found that the velocity of light should be the same in all directions because of the principle of relativity. And it turns out that it solved the Michelson puzzle, but without really addressing it.
Sir?
Good evening, Professor. Welcome to IIT Delhi. It's a pleasure to have you here. So I wanted to ask you about your perspective of Wi-Fi technology, light for wireless communication. Do you think it can become a big thing in the future, and what's your review about it?
About what kind of?
Wi-Fi, wireless technology, light using
Wi-Fi.
Light communication. Light communication. You're thinking of quantum communication?
No.
What?
La transmission pas par les ondes électromagnétiques, mais par le. Okay.
Okay, thank you.
Later. C'est une autre technologie. Okay.
Sir, you have any approach or research in the field of biophysics and bioinformatics in your lab?
No, I have not worked in this field, but I know that it's...
In molecules, biomolecules?
I know that there are questions, conceptual questions and technical questions which rely physics and biology, because physics provide instruments which allow us to test biological systems with high precision, and also because conceptually ideas like the Brownian motion or statistical issues of physics are useful to understand some processes in neurobiology, for instance.
Yeah.
But I am not a specialist at all in this field.
Okay.
Thank you. Next question? Next to the sir. No, next to the sir. No, to the sir after you, yeah.
Good evening, Professor Roche. I just wanted to ask about something which was conspicuous by its absence. Since we were discussing optics, there was a strong objection to Newton's theory of light by Goethe. By Goethe.
Goethe, yes.
And he highly disagreed, so I wanted to know what is the status of his contribution to optics. And the second thing, since we were discussing about the philosophical presuppositions of science, I mean, wouldn't it be can we really say that it is presuppositionless? That's a huge statement to make, because like Goethe gives an example that in science we use hypothesis, and hypothesis is like a scaffolding we use to erect a building. Mm-hmm. But then to go on to confuse the scaffolding for the building would be a problem. Thank you.
Okay, first of all, I know Goethe's contribution to, he wrote a treatise of light, treatise of colors, in which he has a very interesting distinction between physical and chemical colors, but his approach is very qualitative, and of course he criticized Newton, and Newton was in some respects wrong. Now, what I said about philosophy, I don't want you to take it too harshly. You may have some philosophical ideas which can be helpful, but I would say it's by chance. It's not. There is no rational reason for that. You might go in the right direction because you are driven by some philosophical thought which might be right, but they also might be wrong unless they correspond to observations. So I think it's a very difficult debate. Myself, the closest I have been to philosophical question is indeed the question of reality. What is a real measurement? What does it mean to make a measurement? Why does it give a random result? What is randomness? All these are questions that you can find their roots in philosophy, but they also have very clear mathematical definitions. So in the end, I think I prefer to think about some rational explanation, not philosophical ones.
So we have two last questions, ma'am, please.
So you talked about I have two questions. One is, I usually find that the books that we write, like the writers write, they come up with a name and the editors change them. Did it happen in this case as well? And next question is, I read that Husson wrote it, that I do not want to work with Newton because I don't want to be seen that I worked under his shadow, right? But Newton wanted to work with Husson because that is when he refused. So my question is, did Newton had some kind of doubt on his corpuscles theory? I mean, I'm perhaps pronouncing the word wrong. What I meant is, he meant that the light is kind of particles, right? So did he had a doubt that it can be wrong because he wanted to work with Husson and Husson denied it?
I'm not sure I understood. The question is whether Newton believed in Copernicus.
Yeah, No. My question is, did Newton doubt his own theory, the particle one? Because he wanted to work with Husson.
Maybe he doubted it, I don't know. But he talked about the particles of color. He said that it was difficult to explain by reference the fact that the light beam can go in two different directions. So he tried to explain it by some asymmetry of the light particles. So he went very far in this direction, and he never accepted it. He never discussed this, the possibility of wave theory. I must mention that there is another scientist we did not talk about, who played a very important role, who was the most modern one, is Fermat. Fermat gave a principle of propagation of light, which is a least time principle. He said light goes from one point to the other by taking the smallest amount of time. And this led to the principle of least action, which is the deepest way to look at quantum physics nowadays. So Fermat is a strange guy because he was this kind of intuition. He also had the intuition of the famous Fermat theorem in mathematics, which took 350 years to be demonstrated. So this is something mysterious about Fermat. And I must say that I relate him to Ramanujam in mathematics in India, which someone who had some bright ideas. Nobody knows from where the ideas were coming, and it took a lot of time to demonstrate what he had in mind.
Yeah, absolutely. No. There is one last question from Sir. I'm sorry. I'm really sorry. Oh, the book. The book.
Did you come up with this name on your own, or did your editor help with it?
Oh.
What?
Je veux savoir si le titre a été inventé par vous ou par l'éditeur.
The titre,
en anglais, je pense.
The Science of Light, no, it was in French it's called Light Revealed, but after writing the book in this way, I thought it was not a good title because Revealed has this idea of revelation, and I was afraid some people will think that it's a kind of a religious book about light, which is not.
Well, you start against obscurantism, so yeah, that was not a good... Okay.
It's revealed in the sense of revealing on a photographic plate, so it's not religious.
So the last question is for you.
Sir,
Make it short.
Yeah. Good evening, sir. Sir, my question, like, there is always conversation in physics community for the connection between quantum physics and general relativity, which is a deep fundamental question we need to solve. So my question is related to the controversial EPR paper and the entanglement. So I am always fascinated by the entanglement and nature of it. So, and Einstein usually used to say about it that it is a spooky action at a distance.
Yeah.
So if we think about from Einstein and Bohr debate perspective about these single quantum object and their nature, and if I want to hear from your viewpoint on that, and so if we assume the debate question is as follows: if we have two entangled atoms, and if one of atom fall into the black hole, so does the laws of quantum physics still allow to preserve the entanglement between the two atoms, and what happens, these spooking happens, action to happens, and then what happened to the information? So what is your comment on that?
I don't. Okay, I think first of all it would take a lot of time to answer, and second, I'm not a specialist of black holes. But the question you are asking is a question about the compatibility between general relativity and quantum physics, and I must say this is a very hard question. There is no answer now. Nobody knows what happens inside a black hole because one does not have a theory of that. But it's a deep question, and there is a strong connection in physics now between quantum information science and black hole physics, and there are meetings which are devoted to that. Now, you talked about the Einstein definition, the spooky action at distance. There is no real action. You cannot use this for propagating information from one point to the other. What entanglement tells us, not in the context of black hole, is that a system made of two parts which have interacted and are separated is still a single quantum system. And since a quantum measurement perturbs the system, if you do an experiment on one part, it perturbs the system immediately. But this perturbation cannot be used to propagate information faster than light, and Einstein knew that. He never claimed that entanglement was contrary to relativity. He just did not like the idea, but not for that reason.
Yeah, I mean, last question. I thought it will come from the floor, but this is a very standard question. What is a photon?
It's a particle of light.
Is it a particle or is it a wave?
Yes, and this is, so it's a dual aspect. So you might say as a conclusion that Einstein reconciled Newton and Huygens in a strange way.
But you know, the question, you know, this
when light, the way I will answer is when light propagates as a wave, but when it interacts with matter, it interacts as a particle. So that's why it gives rise to interference effect when it propagates. It's why Huygens was right and that light goes slower in water than in air. This is a wave aspect, but when it interacts with atoms, it interacts by packets, by discrete quantities, and this is a particle aspect. And it's time.
Usually we say that in an experiment, you can observe one of the aspects, not both.
Yes.
Has there been an experiment where you have both aspects?
No, you cannot observe both. There have been very subtle experiments. For example, an experiment called the delayed choice experiment. When you do an experiment, an interference experiment, and when the particle has already entered the device, you modify another part of the device which is a bit further away, and still the particle always acts as it should. Either the passes are undistinguishable, it acts as a wave, or the pass can be distinguished and it acts as a particle. So it's difficult to trick nature in this. And quantum physics is a very solid theory. If you try to modify it just a little bit, everything collapses. So it's very difficult to make a theory which will reconcile the wave and the particle aspect without completely destroying it.
Thank you. On those words, thank you so much, Professor Haroche, for your presence.
Thank you.
Thank you. I just hope this 1 hour and a half discussion about science will also make you change a bit, maybe for some of you, the idea you have of France not only as art, culinary, but it's also science and tech. Thank you so much.
This one, it's my pleasant task. Thank you, Professor Haroche and the panelists. It's my pleasant task to present you a memento on behalf of the Institute. Don't know, but right. I should also inform you that on Thursday, Raghuram Rajan will be speaking in the Dogra Hall this time. So you won't have to take up all these complicated asana postures, I believe. And finally, I think there are refreshments outside.